Okay, so the topic for today is the free electron gas, or the conduction electron in metals, right? And this is an application of the Fermi-Dirac statistics. We will apply the Fermi-Dirac statistics to the situation considering electrons in a conductor, right? So let us see what we get if we apply the Fermi-Dirac statistics to electrons in a conductor, right? Okay. It is in the Sears book on page number 407, and it is also in the Reif on page number 388. The free electron. So the basic theme of this application is in a conductor, right? There are like ions placed in a conductor at fixed sites, and there are core electrons that are very tightly bound to the nucleus, and there are some electrons which are not that tightly bound to the nucleus. Those electrons which are not tightly bound to the nucleus, they roam here and there because they are not, that is a picture, you know, there is one picture. Like those electrons which are far away from the nucleus, the valence electrons, they are not very tightly bound to the nucleus. When they are not tightly bound to the nucleus, it is like a situation that they are kind of free, right? Okay, let us just draw a diagram. For example, these are ions. Ions in a metal. They have fixed positions. In K position, fixed position. Right? And there are electrons. There are very tightly bound electrons. According to the free electron theory of metals, conductors, ions are fixed at fixed positions. Their separation distance is constant, right? And the core electrons, they are very strongly attracted to their corresponding nuclei, right? But they are very far away electrons, right? In metals, they are far away electrons. Those far away electrons, which we also call valence electrons, they are kind of somewhere here, 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 somewhere here. And according to the band theory of solids, the energy, the conduction band in metals or in conductors is half filled. And there are allowed energy levels. So that the electrons can be easily excited to the higher energy level, or there is enough thermal energy. हम ये कह सकते हैं कि आम टेम्परेचर पर इतनी थर्मल एनर्जी होती है कि वो रैंडमली वो जो है वाइब्रेट करते हैं या इधर उधर जाते हैं. So we consider these electrons not tightly bound to any of the nucleus. They have kind of equivalent force from each of the nucleus, and they can just move like here and there. They feel force only when they come near the surface. When these electrons, for example, this is the surface. For example, this is the surface. So these electrons cannot escape. There is a potential there. These electrons are, we can say that these electrons are under the average attractive potential of these positive ions. The electrons are under the average attractive force or field of the positive ions. However, right, that is why they cannot escape the surface of the metal, but they can freely move inside the surface of the metal, inside the conductor. For example, ये आपके पास conductor. So electrons, they are valence electrons inside this. Suppose this is a copper cable. So there are valence electrons inside, right? And they are relatively free, and they are, you know, the average attractive force inside this conductor on the electrons is kind of zero, right? But they only feel the force when they are near the surface, and so that force, that average force, that does not let the electron to move out of the surface. So these are free. It is like समंदर में जो पानी है, पानी के मॉलिक्यूल समंदर के नीचे जो है सतह के नीचे आसानी से तैर सकते हैं, लेकिन अगर थर्मल एनर्जी उनकी ना हो तो वो वाइब्रेट नहीं कर सकते, एवापोरेशन नहीं होगी. अगर जीरो पे हम जाए तो एवापोरेशन नहीं होगी, राइट? सो एवापोरेशन कम होगी. तो इसमें ये है कि इसी तरह जो है इलेक्ट्रॉन्स इस कंडक्टर के नीचे काइंड ऑफ फ्री. So we consider them free. There is mass to electron, right? And they have, suppose they just move randomly here and there, randomly, and when there is no applied voltage, so the net motion of the electrons will be zero. Some will be moving in this direction, some will be this direction, and the net result will be equal to 0. So we consider the case of these electrons, and we call them free electrons. So let us apply the Fermi-Dirac statistics to the situation of free electrons, which are in a. Some question?
सर ये बोर्ड नहीं दिख रहा, कैमरा.
हाँ,
ये बोर्ड हमें दिख नहीं रहा है.
बेटा कैमरा तो ऑफ नहीं है मेरा.
ठीक है सर.
आपके पास कुछ फर्क होगा, मेरे पास कैमरा ऑन है.
हो गया सर.
और रिकॉर्ड भी हो रहा है. ओके. सो since electrons are spin-off particles and they are indistinguishable, so we can apply the Fermi-Dirac statistics. Fermi-Dirac. So we apply Fermi-Dirac statistics and see what we know now about the electrons, the conductor. Some new parameter. Do we see some new parameter if we apply Fermi-Dirac statistics to the electrons in a metal, right? So let us apply the Fermi-Dirac statistics, right? So the Fermi-Dirac statistics is the number of electrons right? A number of particles in an energy level I is equal to Gi, right? And e to the power alpha plus beta EI and plus 1, right? Suppose there is equation number 1, where Gi is the number of states in that particular energy level R. Okay. Now, since this is about general particles, Gi is the states, and so we know that electrons are spin half particles, and they have plus spin and they have minus half. So we can say that they are further doubly degenerate. There are, if Gi is the number of states normally, right? When we consider general particles. So if we consider electrons, we can multiply the states by 2 because there is spin up state and spin down state. So they are further 2 states. So we can write this is like Ni is equal to 2Gi by e to the power alpha plus beta EI plus 1. Right. So to see the distribution of particles, we must determine, how much is the number of states? How many states do we have? And according to Pauli exclusion principle, there can only be one particle in a state. So first, the most important thing is how many states we have here. In the conduction electrons, how many states do we have? So we have to find the number of states, right? So for that purpose, we consider a little small cube of a conductor, right? I consider a small cube of a conductor with length L each side, right? Each side is of length L. So the volume of this will be equal to like L cube. L cube will be the volume of the, that small cube that I'm considering. Okay. So electrons are particles. They have some mass, right? But since these are quantum mechanical particles, so we apply quantum mechanics to it, and from the de Broglie hypothesis, we know that there is a wave associated with a quantum mechanical particle, right? And if a quantum mechanical particle has a momentum p, right, mass m and velocity v, then the wave associated with it has a wavelength. If you can recall, they are called matter waves. So the wavelength of those matter waves, right, can be written as H or P, de Broglie hypothesis. De Broglie hypothesis. We know that particles can behave like wave, and if P is the momentum of a particle, then there is a matter wave associated with it, and the wavelength of that matter wave can be obtained from the de Broglie equation. Lambda is equal to h over p, where h is the Planck constant. So we have a wave inside this cube. Inside the cube, we have a wave. So the cube is kind of fixed cube. So a wave will be we can think of the situation here that a wave will be moving from this side here and will be reflected back. So it will be like kind of standing waves because a wave and its reflection, we have already done that in our previous classes. A wave, when it combines with its reflection, it produces a standing wave. So there will be standing waves produced, right? If we try to read the formula for the standing waves, right, from your base, or from our previous classes that we did, it was lambda n was equal to 2L divided by n. The stationary waves are the standing waves which are produced here, right? They will have a wavelength, lambda, and equal to 2 times the length of the cube, or the length of the fixed position, divided by n. And we say those stationary waves are quantized, where n is equal to 1, 2, 3, 4, 5. So these are stationary waves, right? We have done this, and I hope you remember it. So it will be like for n is equal to 1, that will be the first mode. For n, look, for n is equal to 1, if you remember, it was like this. When the wavelength of this wave is equal to half of the length of this separation, or string, you can say, right? And for n is equal to 2, if you remember, it was like this. And this wave, which is moving in this direction, suppose it also interferes with a wave like this, and then it makes a situation like this. So this is one mode, this is another mode, and there will be another mode for n is equal to 3, another mode, and there are kind of a large number of modes. And if you remember, I told you that maximum mode will be equal to the number of particles that are present in, I have done that to you. Vibrating particles. Okay, so this is the quantized wavelength, and this gives us the wavelength of these waves with different modes. Each of the mode, this mode can be considered as a state, one state of the electron, another state of the electron, another state. We are considering electron as waves, right? So these are different states. The standing waves, the modes, different modes of the standing waves, they are different states. So if we put 3 into, right, 4 into 3, what we get from here, P is equal to NH4 2L. P is equal to NH4 2L. And since it is N, there is N, where N is equal to 1, 2, 3, and so on. So our momentum is quantized. The momentum of the particle is quantized. The momentum of the electron is quantized. Right? So let us go further. Now, equation number 5 tells us the momentum of the electron is equal to N, H which is the Planck constant, divided by 2 times L, which is the length. Since momentum is a vector quantity, therefore it can be written as P square is equal to Px squared plus Py squared plus P C squared. And if it is N, so we can write is N is equal to here Nx, Ny, and Z. So Pn is equal to P Nx squared plus Py squared plus P C squared. Since momentum is a vector quantity, right? Or we can say that. Okay. Also, we know that here, from here, right? From here, we can put this value here, right? So P and X will be equal to, we can write it like that. P and X is equal to Nx, or if I put N, H is constant, 2 is constant, and the third thing is like Lx is equal to Ly is equal to Lz here. Lx is equal to Ly is equal to Lz is equal to L. Right? So if we want this to describe it, the momentum in the form of its component, then the option is to split into components. We can do that, and let us try that, right? So this equation Pn squared can be written as 5 in, this is equation 5 in, say this is equation number 6. So if I put equation number 5 in 6, H square will go off, divided by 2L, right? And X squared plus Ny squared plus N Z squared. Right? So we got the momentum, the quantized momentum in this form, L2 with 2L, and X squared plus Y squared plus N Z squared. You know, here it is like your momentum's kind of, momentum is a vector quantity. There could be momentum space as well, or state space, or phase space. There could be like momentum space, there could be phase space. I hope you have done phase space in your classical mechanics, right? And you know, in when you go to Lagrangian from your Newtonian mechanics, right? When you go to Lagrangian from your Newtonian mechanics, you put, you take instead of doing with a vector quantity, you just deal with a scalar quantity, which is Lagrangian, and it is equal to T minus P, kinetic energy minus the potential energy, right? Similarly, and here the coordinates are like velocity and x, y, z. Now we then have Hamilton's equation, and I hope you know that there is an advantage of Hamilton equation over the Lagrangian equation, right? Because in Hamilton equation, you know, we use the generalized coordinates as we use momentum as like coordinate too. So there is like differentiation, differentiating the Hamiltonian with respect to momentum, Px, Py, Pz, etc. So there could be momentum space too, right? in which the whole Hamilton mechanics just moves around the momentum, right? And there are some very good advantages to dealing with Hamilton's equation instead of Lagrangian mechanics, right? One advantage is Lagrange equation is like a second order differential equation, and Hamilton is like a first order differential equation. It's easier to use to deal with first order differential equation instead of a second order differential equation. And the second is like the Hamiltonian equation. Hamilton equation. There are some cyclic coordinates. If some coordinate is not appearing in the equation, then we can right away treat it as constant. So there are advantages of Hamilton equation over Lagrangian or over Newtonian mechanics. Anyway, so momentum is can be considered as it is a vector. So it is quantized here, right? And we can now this equation tells us that the momentum can also be represented in terms of a number space, right? We can write this as Pm is equal to h over 2m and x squared plus n y squared plus n z squared to the power 1 over 2. Let that is equation number 10. So it means like it means that there could be an integer space. I believe we have done this before in one of our topics, but let us do a slight refreshment and refreshing our thoughts from there. So, representing momentum, right, in terms of number space, in terms of numbers, nx and y. So, let us make a number space. N and y and z, and there will be some maximum number as well, right? We have some upper state. So the total, momentum, the number of states depends upon the momentum. Right? Momentum is quantized because we get the wavelength from the momentum. Lambda is equal to h over p. So the number of states, right, is dependent upon p, and p is dependent upon the antigens, right? So the states can be represented in a. We can calculate the total number of states. Our purpose is to find the total number of states. तो हमारे पास एक स्पेस आ जाता है जहां पर हमारे पास 3 कंपोनेंट्स हैं nx, ny and nz. इसमें किसी भी मैक्सिमम n तक जो भी स्टेट्स हैं, that will be like a sphere. It will be like a sphere. It will be like a sphere, and each small, look, or this is equal to 1, this is equal to 0, this is equal to 0, right? This is one space, one state. This is equal to 1 state. 1, 2, 1, another state. 1, 1, 2, another state. So each smallest gap of this much represent a single state in this state space, in which a small q represents a single state. Right? So the total states will be equal to what is the volume of this. जितनी इसकी वॉल्यूम होगी इस स्पेस की उतने ही हमारे पास स्टेट्स होंगे. लेकिन हमारे लिए एक और फायदा है इसमें, हमें सारी वॉल्यूम कैलकुलेट करने की जरूरत नहीं है. राइट? क्यों? क्योंकि ये स्क्वायर है, आपके पास जो मोमेंटम आ रहा है इस ये डिपेंड करता है nx, ny and z पे, and these are squares. इसका मतलब है हमारे पास जो जितने भी नेगेटिव वैल्यूज हैं एन एक्स, एन वाई और एन जेड के, वो हमारे पास कोई नई इंफॉर्मेशन नहीं दे रहे हैं, बल्कि वो वही स्टेट इन स्टेट्स को रिपीट कर रहे हैं. दे आर रिपीटिंग द सेम ओल्ड स्टेट. फॉर एग्जांपल, if I take an x is equal to -1, again the result will be like a +1. If I put an x is equal to -2, again it will be like if I put nx is equal to 2. So it will not be giving me a new state, it will be just a repetition of the same old state. So हमें ये नेगेटिव नंबर्स की वॉल्यूम कैलकुलेट करने की जरूरत नहीं है. और हमारे पास सिर्फ 1/8 अगर पूरे हो जाए, राइट, इस वॉल्यूम का इस साइड मैं इधर तक ले आता हूं. वन एट ऑफ दिस होल वॉल्यूम. इसको मैं कब करता हूं तो हाफ स्फीयर ऊपर जाएगा, हाफ स्फीयर नीचे आ जाएगा, तो आधा आधा हो जाएगा. फर्दर ऊपर वाले के मैं ले लेता हूं और इसमें सिर्फ ये एक क्वाड्रेंट ले लेता हूं, एक वाला, सिर्फ ऊपर में से सिर्फ एक वाला, क्योंकि बाकी में नेगेटिव नेगेटिव आ जाएंगे और नेगेटिव नेगेटिव हमारे पास कोई नई इंफॉर्मेशन नहीं दे रही. सो मेरे लिए सिर्फ ये इस की ही वॉल्यूम काफी है, ये और मेरे पास एक्स्ट्रा है, मुझे इसकी जरूरत नहीं. राइट? सो the number of states G up to some momentum P will be equal to 1/8 of this is the total volume of the sphere in the state in the integer space, and this is 1/8 of it. आधा नीचे आधा ऊपर. सो 4 नीचे 4 ऊपर, जब आपने आधे को उसमें डिवाइड किया. मैं आपके लिए एक पोल लाया हूं ताकि आपको दिखाऊं. ये मेरे पास कंप्लीट स्फीयर है. ये नारंज में आई हैव जस्ट broken a small orange for you, right? मैंने आपके नारंज तोड़ा. सो इसको ये दरमियान में काटें तो XYZ आ जाता है, राइट? मेरे लिए सिर्फ ये काफी है. ये 1/8 हो गया आपका, ये काफी है. ये वॉल्यूम ये मेरे लिए काम के जो है स्टेट्स दे रहे हैं. बाकी इसमें nx नेगेटिव आ रहा है, इसमें ny नेगेटिव आ रहा है, दूसरे में nz नेगेटिव आ रहा है, सारे इसमें जो है वो वगैरह वगैरह. तो मुझे नेगेटिव सारी चीजें जो है कोई नई स्टेट नहीं दे रही, जस्ट ये काफी है. 1/8 of this sphere, that is enough for me. Okay, so this is a question number. Okay. Let me put 5 in. Okay. Right. So GP will be equal to 1/8 4 over 3 pi, right? And for n cube, I write Q and P n, right? And divided by H and whole cube. n की जगह मैंने इक्वेशन 5 से ये लिख दिया 2L P n divided by H. This will go with H, right? So it will be equal to 4 over 3 pi, right? V P n cube divided by H cube. H cube. Gp is equal to 4 over 3 pi. V is volume, which is equal to L cube. P n cube divided by H cube. Right? That is the now that is the states, number of states, right? In terms of the volume of the sphere, right? In terms of the volume that we have considered our original, we are going to our original volume of the sample, right? And Pn to quantize momentum, right? So this is giving us the states, the number of states, because we know this, we know this, we know the volume that we first considered, or small cube, right? And Pn. Now we want to convert Pn to energy, but before that, right, we do a little trick. We say there are a large number of electrons as well, and a large number of states. A large number of momentum, a large number of momentum, right? A large number of momentum. And when there is a very large number of momentum, right, then we can consider them like continuous. We can consider these as continuous, not as quantized, for the very large number of electrons and very large states. We can consider this as continuous. So for continuous, we can apply calculus, a little calculus to it, right? So the number of states between P and P plus dP. The number of states between P and P plus dP, some small increment dP, right? P से लेकर P plus dP तक हमारे पास कितने states आएंगे? So I will just differentiate this from equation 9, right? Equation 9 applies. G is a function of, which is a function of P into dP, right, is equal to 4 over 3 pi. V is a constant, H is a constant. The only thing is, like, we are differentiating, that is with respect to momentum. I think it will become 3p square dp, and 3 is 3 के साथ cancel हो जाएगा, right? So what I will get will be equal to 4, right, pi v p square dp or h. Now I have considered, I have changed the discrete situation into a continuous situation, continuous variable, and such that we can apply a little bit calculus. Okay, now let us move from momentum to energy. We know that E is equal to P squared divided by 2m, right? And P is equal to 2m squared, right?
Excuse me, sir.
Yes.
Sir, h cube नहीं होगा.
Oh yes, thank you. Thank you.
और
Thank you so much. Huh?
p के साथ सब्सक्राइब में n नहीं लगेगा.
Oh, okay. We just changed it from, it was n was making it discrete. And we said we are changing from discreteness since, the large number of states, n is equal to 1, 2, 3, 4, 5, go on to very large number of particles, large number of electrons. So we then say the separation will be very small, and therefore we can remove the discreteness और इनको जो है वो continuous consider करते हैं. Like जैसे कि आपके पास रेत की ज़र्रात हैं, तो आप इसको जो है वो अगर हम अपने उससे देखें तो रेत की ज़र्रात को अगर हम छोड़ें तो हम कंटिन्यूस कंसीडर कर सकते हैं अगर इसको बड़े पैमाने पर देखें. यानी रेत की ज़र्रात हमारे पास एक बिग बॉक्स में है और बॉक्स का मुंह थोड़ा सा खोल दें तो रेत की ज़र्रात एक फ्लो में जो है वो बह जाएंगे. तो हमने इसको डिस्क्रीटनेस को हम उसको कंटिन्यूटी में चेंज कर रहे हैं. Therefore we don't need n now.
Okay, sir.
Got it? Okay. So we don't need n. Okay. So P square is equal to 2m8. Right? Let them be the equation A and dp from here. dp will be equal to, right, 1/2 square root m square root, right, and e to the power minus 1/2 into dE. When इसको differentiate किया, right, 1/2 and 2 इसके साथ cancel हो गया तो square root आ गया, right, and अपने square root में आ गया. Now e to the power 1/2, so minus 1 will make it minus 1/2. That is B. So now we put A and B into equation number 10. Okay, A and B in number 10. So what we get? G of E, right? G of A if is equal to G of E. So G of E, I'm changing it to it, and that will be equal to 4 square root of 2 V by x cube m to the power 3 over 2 e to the power 1 over 2 into dt. Right? If we take this as a constant, if I call it C, right? So G of A dE, the number of states between energy E and E plus E, where E is the energy of the electrons, right? So the number of states between energy E and E plus dE. And when we take this as C, some constant, C, because this is constant, this is constant, this is, all of them are constant. So it is equal to e to the power 1 over 2 and 2 d e. Right? With that is equation number 11. Now put 11 in. Put 11 in equation number 2. Right? So since I have removed the discreteness by the continuity, I do not write Ni. Now N is a function of E. So I can write the number, right? Ne, GE, the number of particles. In equation 2, gives me the number of particles per energy level. This is also called the occupation number, right? 2 and to for G of E, right? I would like 2C e to the power 1 over 2 dE divided by e to the power alpha plus beta plus 1. Now we have written the number of particles between energy E and E plus dE. This is equal to 2 times C, and look, there is a square root of E. So it looks like the number of particles is a square root function. The states are also a square root function of the energy. Look at this equation number 11. The number of states varies as the square root of energy. Right? Okay. Now, we don't know. Oh, here is E. Beta E. मैं भी भूल गया था. Right? So there is an E as well. Beta E. So now, this is constant there we know, but we don't know alpha plus beta. And we know from our previous discussion that beta was equal to, beta किस चीज के बराबर था आपको याद है? हाँ?
1 over P.
1 over kT, right? Thank you. Beta was equal to 1 over kT. And मेरे ख्याल में हमने अल्फा को भी कैलकुलेट किया था. याद है आपको कुछ ना कुछ? हाँ?
Sir, nu over kT.
Very good. Great. हमने इसको जो है वो उस पर एक कंडीशन लगाया था, उसको सम किया था. इसको हमने सम किया था, राइट? इसको हमने सम किया एंड टोटल the summation is equal, जिसको हमने n कहा, summation को इस पे अप्लाई किया, जो हमारे पास फर्मी डिराक स्टैटिस्टिक्स है, उस पे हमने summation को अप्लाई किया, राइट, एंड हमारे पास हमने जो है वो इसको उसमें लिया e to the power alpha n is equal to z, और फिर हमने z को पार्टीशन फंक्शन दिया, पार्टीशन फंक्शन है ना, पार्टीशन फंक्शन लिया, राइट, and kt log of z, right, divided by minus kt, and if you remember that was equal to Fermi energy, right? So अगर आपको वो नहीं आता तो मैं आपको वो कर दूंगा, लेकिन मेरे ख्याल में ये हमने डिराइव किया था। तो अल्फा वाज इक्वल टू म्यू और kt, हमने प्रीवियस में इसको, प्रीवियस केस में आप पीछे जाएं, अगर नहीं है आप उसको देखें, आप मुझे ईमेल कर सकते हैं, यू कैन कॉल मी एनी टाइम इफ यू हैव सम डिफिकल्टी एंड वी विल डिस्कस इट, राइट। सो if there's a problem again, you go back to your notes. If there's a problem, we can discuss it again, right? And that is like, this is obtained from the condition Ni is equal to, इस condition को on Fermi Dirac, इस condition को आप Fermi Dirac statistics, sorry, distribution function पे apply करें इसको, तो you get alpha is equal to mu over kt. It is equal to minus mu over kt. Now it was minus mu over kt, right? So do you remember what was how did we define the chemical potential? Mu is chemical potential, right? So it was like the amount of energy required to add a particle to a group of particles. If you remember, partial f, if f is the free energy, it was equal to partial f by partial n, the amount of energy required to add a particle to a group of particle। आपको याद है मैंने आपको कहा था कि अगर आप इस रूम में बहुत सारे लोग बैठे हैं तो एक बंदे को बाहर से रूम में जो है वो घुसाना, राइट, ये इसको कहते हैं केमिकल पोटेंशियल। अगर लोग ज्यादा हैं उधर, इट विल बी डिफिकल्ट टू पुश दैट पर्सन इन द रूम, अगर लोग उधर लोग कम हैं तो दैट विल बी, you know, it will have a small chemical potential. So kind of like the number, the amount of energy required to aid a particle to enter into a system. So that was the chemical potential, right? Now we want to deal with the chemical potential here and just introduce a new name, something else, a new number, which is related, right? A new parameter. A new parameter which is related with conduction in metals, and it is called the Fermi energy, EF, Fermi energy. Fermi energy कहाँ से आया? So look, आपके पास you have states, and according to Fermi Dirac statistics and the Pauli exclusion principle, only one electron can occupy a state. So नीचे वाले states में एक electron आ गया, then the other should go to the higher energy, right? At t is equal to 0. Suppose at t is equal to 0. At t is equal to 0 K, every electron will try to be in the lowest energy state. So we'll try to come here, this level. But there will be only one electron. So then he will move to the other, the second one will move to here. The third one will move to here. The fourth one will move to the next, and so on, so on, so on, until all the electrons occupy the states. Right? So the highest energy, right, which is filled, the highest energy level which is filled, the energy of that level at T is equal to 0 is called Fermi energy. Suppose ये हमारे पास EF है. The energy of higher or uppermost filled level at T is equal to 0 K is called Fermi energy. Right? तो हम केमिकल पोटेंशियल को, चूंकि अभी ये ज्यादा, अभी ये सारे फुल हैं, इसको फर्मी एनर्जी. अगर आप और इलेक्ट्रॉन लाएंगे तो यू हैव टू, आपने जो है वो इधर कोई चीज आपने इधर लानी है तो जमीन से आपने उठा के यू हैव टू ब्रिंग इट हियर. So you have to apply some energy. So then you have to apply energy to bring it here. Then to apply energy to bring it at the top. So the energy which is required now to add an electron here is the same as like the chemical potential is the same like the Fermi energy. So we can now replace the chemical potential by the Fermi energy, right? So mu will be equal to Fermi energy. Fermi energy. This is something new that we are doing, right? So mu will be equal to EF. Therefore, equation 12 can be written as, equation 12 implies that, right, N of E DE, N of E DE is equal to 2C, right, e to the power 1 over 2 D of E and e to the power, right, E minus EF or KT and plus 1. Now हमारे पास number of particles in some energy interval dE will be equal to this thing. This equation 13 gives us the number of particles, how they occupy different energy levels. This is giving us, this is the rule now, how the electrons will occupy energy levels in a conductor. This is given by this equation. In the number of electrons in an energy interval dE will be equal to, and it varies in the square root of energy as well as it depends upon the temperature. What is the temperature? Right? So this is an important equation. Now from here, we can find the occupancy.
Sir,
Yes?
is there any difference between chemical potential and Fermi energy? Is there any difference between chemical potential and Fermi energy?
Okay. Look, in this situation, the chemical potential is like The Fermi energy, or the Fermi energy is like a chemical potential. So the Fermi energy is equivalent to chemical potential, but chemical potential is a very wide concept, and it is not only bound to free electrons. We define chemical potential in any situation, you know, for chemistry, for physical particles, for molecules, we can define chemical potential. But free energy is only related with electrons. You know, free energy is only related with electrons. So here, in this situation, free energy is equal to chemical potential. Our chemical potential is equal to free energy. But chemical potential is not always equal to free energy if the system is different. If our sample is different, हमारे पास कोई gas molecules, right? Then chemical potential will not be equal to free energy. Then we will define chemical potential, chemical potential will then not be equal to Fermi energy. Then we define the chemical potential. We define it like that. Right, we define it here. Is it coming? There is some noise coming. I don't know if it is coming from here or somebody has his mic on. So, did you get the difference between chemical potential and the Fermi energy?
Yes, sir. Thank you, sir.
Okay, thank you. Now you can turn off your mic. Okay, so our next class, and that should be the last class. If we take the next class, मेरे ख्याल में या तो मैं आपको 2-3 पेजेस के नोट्स दे दूंगा, और मेरे ख्याल में क्लास लेने की भी जरूरत नहीं है, 2-3 पेजेस के जो नोट्स है मैं आपको दे दूंगा, और वो जो है हम उसमें ये देखेंगे कि how the number of electron changes with energy at different temperatures. Right? हम एक दो ग्राफ भी बनाएंगे. So that is the last kind of second last topic for you. We get the distribution function of electrons in a conductor. This gives us the distribution function of electrons in a conductor. If there's any question, then we can discuss. Anyone wants to say something? If not, I will stop the recording. Okay, see you then.